Hi, this is Gilbert Mendoza, and I'm a security architect with Cisco Systems, and today I'm going to show you how to implement a Cisco Secure Firewall running in transparent firewall mode. There's a number of reasons why you might want to run a firewall in transparent mode. One of the advantages of a transparent firewall versus a routed mode firewall is that it's completely invisible to the devices surrounding it. In a routed mode firewall, which is typically what most administrators are familiar with, you have to assign IP addresses to interfaces and then point all of your hosts and network devices to those interfaces, and so that it can direct and steer traffic and control traffic. This can be problematic for a number of reasons. Firewalls typically aren't the best routers, and they may often lack some routing features that your routers enjoy. A transparent firewall just lets those hosts and network devices participate in the routing protocols that they choose, and you don't have to redesign your layer 3 routing topology to implement it in this fashion. So let's show you a couple different scenarios that we can implement a transparent firewall in. The first is the traditional server VLAN segmentation project, where you want to protect servers and place them behind a firewall, but you don't want to change all of their IP networking schemes. So the way we're going to do this here is illustrate it in a small environment using a Raspberry Pi server, and it's connected to a layer 3 switch. Now the server here is called RPi4. On the left, it has an IP address of 10.4.4.10, and its default gateway is an SVI, or virtual interface, on the switch of 10.4.4.1 for VLAN 400. If you look at the interface configuration on the lower left-hand side, it is a typical switch port mode access port, and it is directly assigned to VLAN 400. Now the switch also has a few loopback addresses, just so we can test additional routes and communication beyond the default gateway. So how do we insert a firewall between the server and its own SVI, right, without actually unplugging the server and jamming a firewall in between, right? So we're going to do this creatively with a transparent mode firewall, and we're going to configure the switch ports and the firewall ports to be in a port channel. This will be a trunked port channel, so we'll have sub-interfaces on the firewall, and we are going to leverage what's known as a bridged virtual interface, or BVI, and we're going to bridge multiple VLANs together. This is where the magic happens. We have a brand new VLAN that we're going to create. This will be VLAN 401. We're going to call it protected. You can think of the original server VLAN as the outside interface of a firewall, and this new protected VLAN as the inside interface of the firewall. And the switch, when you create the VLAN, doesn't have any IP addresses associated with the protected VLAN. It's just a non-routable VLAN. But the bridge virtual interface will have port channel sub-interfaces, port channel 1.400 and port channel 1.401, and it will be connected to both of those VLANs, and it will bridge any traffic that comes into VLAN 401 destined for an address on 400, and it'll bridge it across. So this, the process involved in swinging this server over to the protected network is as simple as changing the access VLAN statement on the switch port. We just change it to VLAN 401. And suddenly it is behind this firewall in this protected network. You don't have to change the IP address on the server. You don't have to change the default gateway at all. It's now just behind this firewall. So let's show this in action by going to the switch, show VLAN brief. You'll see that we have two VLANs. This is VLAN 400, servers 401, protected. We have one switch port that's on VLAN 400. If we do a show run interface gig 105, you'll see that this belongs to that server, RPi4. It's on VLAN 400, and it has a port fast statement to allow it to come up very quickly. If you look at our interfaces, the layer 3 interfaces on the switch, show IP interface brief include 10 dot, you'll see that VLAN 400 SVI, that's the default gateway of that Raspberry Pi server. And then we have the loopback addresses for those other networks that we were going to be testing. All right, and if we want to test pings, you can see that our Raspberry Pi server can ping our own default gateway, port route 1. That, of course, works. And I have a little test script called test ping, and it just pings all 4 of those addresses 20 times, and it comes back 20 times as well with no packet loss. All right, so we haven't done anything right now in terms of transitioning this Raspberry Pi server. It is currently sitting on 400 unprotected. Before we transition the server over, let's take a look at our firewall. This is Firepower Management Center. It's our centralized GUI for all of our Firepower software-based firewalls or hardware-based firewalls. The firewall at the bottom here in our what's called Pi Lab is a Firepower 1010 appliance. You can see that it is running in transparent mode. And let's edit the firewall to see how it's configured. We have the interfaces tab, and we can see all 8 physical ports that this firewall has. And we've already configured a port channel interface. You see this is an Ether channel type. And if you edit that interface, you can see that it doesn't have a name, doesn't have any zones on this. Here's the Ethernet, the channel ID. And here are the 2 interfaces that are assigned to the port channel or Ether channel 1.1 and 1.2. The one thing we have configured on here as well is LACP mode of active. Let's take a look at the switch side of things. So, Ether channel summary, if I can spell right. You can see that we have 1 port channel defined. LACP is the protocol, and our 2 physical ports are assigned to the port channel. Show run interface port channel 1 shows that it is the Firepower 1010 appliance, and it is in switch port mode trunk. So we're going to allow multiple VLANs on this switch port, and we have it running in port fast edge so that we can converge layer 2 as quickly as possible on this interface. Now, of course, for security purposes, you can also do a switch port allowed VLAN statement to restrict the firewall to particular VLANs, and that would be best practice. So let's go back to our firewall, and you can see that we have 2 sub interfaces that are designated for this particular lab. The first one here is port channel 1.400. This is the server segment. Think of that as outside. So I call this servers-400. It's part of a zone called Pi Lab servers. Port channel parent interface, sub interface ID of 400, VLAN ID, we specify that so it can be tagged at VLAN 400. On port channel 1.401 sub interface, exact same concept. Here's the protected designation. Think of it as the inside network, and our zone of protected, port channel 1, VLAN 401, and the sub interface ID. There's no IP addresses associated with this sub interface at all. It's just a layer 2 interface. Now at the bottom of this screen, you see we have a BVI. This is a bridge virtual interface. We edit that, and we add port channel 1. Oh, that's actually the wrong one. BVI 2. We have port channel 1.400 and 1.401 bridged together. The only other thing that we need on this BVI is an IPv4 address. So this is not meant to point your host at all to this IP address. We just need to have an IP on that subnet that we are working with at layer 2 and layer 3. So 10.4.4.254 is a high unused IP that we're statically assigning to this BVI. Now our access control policy for this server segment is pretty simple. Once we transition the server into VLAN 401, at the bottom here we have 2 rules that pertain to this lab. We see that we are allowing rule number 3, protected servers ICMP. Anything coming from the protected zone go into the outside server zone from the source network of 10.4.4.0/24. We're going to allow the ICMP protocol to go through. We're also going to allow HTTP, anything coming from the protected network to the server network on that IP address scheme, HTTP and HTTPS, we're allowing that. So just pings and HTTP for a very simple test. At the bottom, we have a default action of block. So notice we don't have any inbound traffic defined. So anything coming from the outside server network and beyond will not be able to go into the protected network. All right, so traditional firewall mode. So let's go to our event table, and we're going to transition this over to the protected network. Let's click on Go Live. And let's go to our switch and type in config t interface gig 105. And before we do that, let's set some pings going. Sudo ping -i 0.01. Let's do 10.10.10.10. This is just going to do a very, very fast ping to see how many we drop when we do this transition. So back to our switch, we're going to type in switch port access VLAN 401. And just like that, we are behind the firewall. Let's go to our firewall. Hit refresh. And we now see we have ICMP pings coming from 10.4.4.10 to 10.10.10.10. Expand that open here. You get more details about timestamps, ingress zones, egress zones, access control policy, which particular rule. We see that this is hitting the protected server's ICMP rule, and how many bytes are involved in this flow. Excellent. Now let's also go back to our server. Let's do Control C. You can see that in this transition, we actually sent 6,000 packets, so 6503. Actually, we sent 6505 and we got 6503 back, so we only lost 2 pings in a very short amount of time. So really, really fast transition. Let's also test secure shell. So let's do web traffic. So do curl -v 10.10.10.10. And you can see we actually got an intelligent HTTP response back from our switch. It's unauthorized, but we still made it through. Let's go back to our firewall. And let's do refresh. And you can see right there, that's our HTTP traffic from 10.4.4.10 to 10.10.10.10 on port 80. It's a web browsing application, and we can see the rules that we hit. We also see that we're using curl 7.64, so a lot of application detail and host-based detail. So let's go back to our diagram here. How can we protect other servers now? If we want to add any additional servers to this protected network, simply change their access VLAN statement to VLAN 401, and now they are protected as well. Any traffic coming from these servers out beyond that BVI will be protected by the access control policy. Now, another thing to note here, servers talking east-west, so Raspberry Pi 4 to Raspberry Pi 5 on that same VLAN are not going through a firewall. They are using just a layer 2 fabric to communicate directly. If you want to protect east-west between these servers, then what you can do is simply add another protected VLAN, maybe VLAN 402, and you can place one or more servers on that VLAN. What that's going to do is allow those servers to be protected out the same way they were before, but in order for them to communicate with each other between 401 and 402, they have to cross that BVI boundary. So you're adding multiple port channel interfaces to the BVI to be bridged, and you are creating separation through the layer 2 network. In this next scenario, what we're going to do is insert a transparent firewall between a number of routed interfaces of a layer 3 switch. Now, a picture will probably help explain what we're trying to do here. In this example, we have a couple of servers on both sides of a layer 3 switch. We have Raspberry Pi 1 on the left with an IP address of 10.1.1.10. It's part of the 10.1.1/24 network block, and it is directly connected to a routed physical interface of gig 101 on the switch. That interface has been assigned the 10.1.1 IP address, and it has the no switch port statement. So this is a physical layer 3 interface now on this switch. On the right hand side, the exact same configuration has been given with Raspberry Pi 2, that's 10.2.2.10, and its default gateway of 10.2.2.1, which is the physical gig 102 interface on the switch. So if we are now trying to insert a firewall again to this switch, how do we accomplish that in this scenario? Because when a packet hits that physical interface, the routing table is going to be looked up on the switch, and it's going to be express forwarded out to the next hop interface of gig 102 if it was coming from Raspberry Pi 1. So what we're going to do is introduce another concept. Before we do that, you may be wondering, well, how, why would we configure our network in this way? Well, we're trying to illustrate another example that happens if we're trying to install a firewall in a segment that has, let's say, a routed WAN service edge. So in this example, we have a couple routers. They're connected to WAN 1 and WAN 2. And on the inside of those routers, we have physical interfaces, of course, connected to other interfaces on the core switch that may have a similar configuration. So no switch port statements, routed IP interfaces on your core switch. And if we want to install a firewall between that WAN and your core, again, this is really the same thing as what we're illustrating here. How do we do that? There's a couple different ways. You can do something very similar to the previous lab, where instead of configuring your physical interfaces on the switch with IP addresses, you can then convert those to SVIs, and then now you have a VLAN that is kind of your edge, and then your two WAN interfaces can come in and they can be dropped in those VLANs, and then you can insert the firewall just like we did in the previous lab. That's one way to do it. Now another way is by breaking up the routing table on the core switch so that you don't have to rewire anything. You can do this all virtually. So what we would do is use virtual route forwarding tables, or VRFs, and in this case we're going to create two. We're going to create VRF1 and VRF2, and then we're going to assign gig 101 to the VRF1, and then gig 102 to VRF2. Now, just like this, we've broken our routing, right? Now these two VRFs, they can't communicate with each other, right? So I'm just explaining this serially so that you can understand exactly how the process is going to work. But this will be done very quickly with minimal downtime. The next thing that we're going to do is create two VLANs, an inside VLAN and an outside VLAN. VLAN 301 will be inside, outside will be VLAN 302. And each of these VLANs will have SVIs. These SVIs of 301 is going to be associated with VRF1. SVI 302 is going to be associated with VRF2. And you'll notice here that both SVIs share the same network block. So 10.3.3.0/24 is actually going to be existing on two different interfaces, which normally would not be possible with a single routing table. But because we're using VRFs, we can do that. They both can exist at the same time. Now, they still can't communicate with each other because what we need is to be able to bridge VLAN 301 to 302, and that's where the firewall comes in. The firewall, just like our previous lab, is going to have a port channel interface, layer 2 trunk, and we're going to create sub-interfaces, one on VLAN 301 and one on VLAN 302. It will be associated with this new 10.3.3.0/24 network, which I'm calling our new transit network or secure transit network. And it becomes very easy for you to plug other segments into this transit network to be behind a firewall. So now anytime a packet comes in from Raspberry Pi 1 on the left to its default gateway, it's going to look up the routing table for its destination. In this case, if it's going to look up Raspberry Pi 2, that 10.2.2 network is going to have a route in VRF1. Where do we get to that? Well, we have to point 10.2.2.0/24. We have to point VRF1 to the SVI 302 on the other VRF. That'll work because of the bridge virtual interface. Now we have to do the exact same thing for the reverse traffic. VRF2 has to have a route to the 10.1.1/24 network, and that needs to point to SVI 301 on the other side of the bridge. So we're using static routes in this example. Of course, you can use dynamic routing, and all the VRFs within this topology can communicate with each other via dynamic routing protocols to make this incredibly scalable and highly available. So let's show you how this is going to work in our lab. Go to our switch config. We type in show VLAN brief, include 3.0. You see that we have VLAN 301, that's our inside network, and then VLAN 302, our outside network. There's no physical ports assigned to that. These are just SVIs within the VLAN. And we are going to look at our interfaces. So IP interface brief, anything with a 10 designation, we see that VLAN 301 interface has been assigned 10.3.3.1, and then VLAN 302 has been assigned 10.3.3.2. We also have our physical interfaces, gig 101, that's going to be 10.1.1.1, and then 10.2.2.1 for 102. Now, if we look at our routing table, let's do show IP route, begin 10. You'll see here that we have two connected routes. This first connected route is 10.1.1.0/24. That's on the the Gigabit Ethernet 101 interface. The second connected route is on the other interface, but we don't see the 10.3.3 network. Why is that? Well, that's because this is the main routing table, right? We've already split up the VRFs so they exist somewhere else. So the cool thing is I've already configured all of the VRFs, everything's ready to go, but we haven't interrupted any traffic flow just yet. So if we look at the routing table, if we do show IP route VRF inside, you'll see here that we have a single connected route. That's 10.3.3.0/24. The inside VLAN is VLAN 301, and that interface is associated with that VRF. We can do the exact same thing for outside. And you see that its connected route 10.3.3.0 is also available. It's the exact same network on both VRFs, each with different VLAN interfaces associated with that VRF. Now you'll notice here that the inside VRF has a single static route that we've put in for the lab. So VRF1 needs to know where 10.2.2 network is. And we're going to point that to the IP address on VLAN 302, which is down here in the other VRF. Same thing down here. So the outside VRF has a static route of 10.1.1.0 for the opposite network. And that's going to be pointed at the 10.3.3.1 interface, which is VLAN 301 interface over here. So just by itself, this is not enough to communicate. You need to have the bridge for this to work, right? And that's where the firewall is going to come in. This is easily configured in show run include IP route. You'll see here I just added those two routes very easily with the IP route statement specifying which routing table I'm inserting those routes in. All right, let's take a look at our firewall config. Go here. Let's go to devices, device management. Here's our Firepower 1010 appliance. And you'll see our port channel. And we have port channel 301, 1.301. That is the inside network. So we've just given it a name of inside 301 to be easily identified. PyLab inside network. Port channel 1 is a physical parent interface or logical parent interface. subinterface ID of 301, and the VLAN ID of 301. And then 302 is going to be here outside 302, the zone, port channel, 302 sub ID, and the VLAN ID of 302. Then down below we have the BVI, BVI1, edit that. You can see that we have port channel 1301 being bridged to port channel 1.302. The IPv4 address we've specified for the BVI is 10.33.254. So again, you're not pointing any host to this IP. It is just used so that the BVI can interoperate with layer 2 and layer 3 bridging. Now, let's go ahead and do a transition. Let's go to our analysis. We're going to look for events. And we will go live. And I have a quick go live script here that we will reference. The go live here is we're going to go into config terminal. We will go into interface gig Ethernet 101, and we're going to add gig 101 to the VRF forwarding inside statement here. Now, when we add an interface to a VRF, it actually removes the IP configuration, so we have to re-add the same IP address that it had before directly to the interface. Then we do that for gig 102. We add it to the outside VRF and add the IP address back to the interface and end. And that is all we need to go live in this environment. Let's go to our switch and let's get ready to cut over. We're going to let's do sudo ping -i. We're going to go to high rate of speed, and we're going to ping from Raspberry Pi 1. We're going to ping Raspberry Pi 2. And we're going to ping Raspberry Pi 1 from Raspberry Pi 2. And now on our switch, let's paste in our config. And just like that, we have been cut over, and you can see that the servers are still communicating. Let's go to our firewall log, and you can see here that we have our communication flows showing in our live log. I just pause it right now. Let's go back to live. You'll see here that this bottom one is 10.11.10 going to 10.22.10, and you can see which zone it came in and out of, access control policy, and it's hitting our permit ICMP rule. You'll see over here we do have a block, but this is actually related to the switch. This is coming from the 10.332 network pinging the destination IP address. We don't have a rule defined for anything else to communicate other than these two servers, so the firewall is working. This last one up here is in the opposite direction, 10.22.10 going to 10.11.10. Very cool. So let's go back to our Raspberry Pi servers and let's Control-C that. You'll see that we only lost about 10 pings in that transition, and I am going, I'm pinging pretty quickly. Let's go to our other server and lost just about the same, maybe like 9 pings in that example. So pretty quick. Something to note about the firewall, I also wrote a rule that says that the Raspberry Pi server should be able to communicate via secure shell. We're going to do 10.2.2.10. And you can see I'm getting a password prompt, which means I should be able to log into Raspberry Pi 2 from Raspberry Pi 1. And Raspberry Pi 2, however, it will not be able to do the same thing. And you can see that it is now timing out. We go back to our firewall logs. You'll see that we have one secure shell being successful, 10.1.1.2.10, or sorry, 10.1.1.10 to 10.2.2.10, and Raspberry Pi 2 is being blocked. All right, excellent. Now let's go back to our presentation and let's wrap up some of these thoughts. This is easy for us to insert into the network in this way and also scale. As you can imagine, these particular core segments can be pretty sizable in terms of how much traffic you need to traverse this fabric. So adding additional ports to the port channel is great. The Cisco firewalls also allow you to go into a clustered mode, so you can actually go up to 16 wide depending on the firewall platform that you have, and scale sideways. If you want to add additional segments to this BVI, very easy for you to do. Just add additional VLANs, add additional sub interfaces, and now you can have multiple segments all traversing this new secure transit network. And their flows will be controlled via a single access control policy. So with that, thank you very much. If there's any questions, feel free to reach out, and it has been great working with you today.